to those who are here in person, you'll notice that there's some sandwiches and chips in the back, so do help yourself. I'm really pleased to introduce Michael Weeks, who is visiting us from UC Irvine. Michael builds mathematical and computational models of cognitive processes. He's done work on memory, semantic cognition, decision-making. The benefit of this, let's say, analytical approach is that it allows you to formalize mental processes with rigor. And through that, you can better understand, say, individual differences, the effect of, say, cognitive impairments, even the effect of situational or task-related variables. I myself have been very influenced by his work on memory and decision-making, though today he'll be talking more about memory impairment, I believe semantic memory impairment. So with that, welcome. If anyone in Zoom has a question, you can just put it in the chat. You can raise your hand. I'll be monitoring it until I can ask it for you, or we'll find some way to communicate the question to Michael.
Thank you, Sadiq, for the introduction. Thank you for the people who are here in person. It's nice to be anywhere in person, and thanks to the people on Zoom who are joining. I think a lot of academics draw a distinction between basic and applied research. Basic research where you solve hard scientific problems because that's the fundamental job of academia, and applied research where you try and serve society by taking solutions that exist in academia and you can see how that could be applied profitably in the real world sometimes. An approach I like, and a phrase I was introduced to by Duncan Watts, is solution-driven science, which tries to be the best of both of those worlds. The idea is that on day one, you find the problem in the real world that needs solving, but it's not a problem that's already been solved in academia. You need to take it back into your research lab and perhaps do basic science and perhaps investigate it for years with controlled experiments or whatever to solve it. I think what's nice about that is, first of all, if you do make some progress back in the lab, you know what the application is. It came from the real world in the first place, so you have a natural application. But secondly, sometimes it can shake you out of the things that just get studied in academia because that's what everybody else studies. It's a way of generating a rich source of new academic problems to be solved. One of those that I hope I've been working on in that sort of mode for a while is the one of memory impairment. I don't think we need any convincing that society would like to understand how memory changes with aging and with impairment, and not just memory, but how we behave or how we make decisions consequent upon that underlying change in our memory systems. What strategies do we use to cope with this underlying change? And this is fairly low-hanging fruit for a solution-driven approach, because the types of tests that are used in memory assessment, the types of cognitive tests like recall tasks and recognition tasks and other judgment or fluency tasks, are almost exactly the ones that were studied in academia anyway. There's a natural throughput where if you can understand the academic problems well, you can make a contribution to the assessment and understanding of memory in clinical practice or other real-world settings. So I've been working in this mode for a number of years with a medical informatics company based in Newport Beach, very, very close to the university in California, who is associated with a Hoag system, is associated with a clinical practice, and has a rich treasure trove of tests of the sort of recall and recognition tasks that are familiar to many people in this audience. And most of these were, for example, in recall tasks, you get a random list of words semantically controlled. So pelican, boat, shoe, pencil, and you have to recall them later. And I've been working on applying memory models and trying to help the medical informatics company in that. And then just before COVID, I went to a conference that was organized on my campus called Memory and Meaning. I find, maybe you do too, most academic conferences are a little too narrow and you wish they would broaden out, stop being so much X plus epsilon. This conference was perhaps a little too broad, but it was interesting in that people from every department and every school on campus who were involved in memory and meaning came along. So we had the usual suspects from neurobiology, or people studying hippocampal cell encoding in rats and things, or the eyewitness testimony people. But there were also people from investigative journalism, for example, who are interested in how do you interview somebody to generate their memories and write a story or an autobiography. Or you had people from classics going through Greek literature that involved these alliterative techniques where characters recited the names of their families, and this was an important part of the structure of the story. So as I said, it was probably a little too broad. It's the only talk I've ever given where literally I followed a speaker who talked about shamanic healing and played the bongos for most of his presentation. But I felt slightly guilty about some of the stuff I was about to present, because these people were talking about the rich structure of memory and meaning, and I was going to have people going pelican, boat, shoe, pencil, which seemed a long way divorced from the sorts of things they are interested in. So I ended up drawing a figure like this in XKCD format to sort of apologize for what I was about to present, showing in a joke way the deaths by Gabor patches, the sort of stimuli that physicists, psychophysicists use, with somebody yelling out these random word lists. And I kind of tried to justify that because we're scientists, we need these controlled stimuli to probe the memory system, just like vision scientists need a Gabor patch to probe the visual system, even though people don't go around seeing Gabor patches very often in everyday life. And it was at that point I thought I really should pivot this research a little bit. Some of the testing that's done in clinical settings is not random word lists. They're tasks that are associated with semantics and meaning, and maybe I should start studying those tasks in this model-based way. And so that really brings me to what this talk is about. It's using cognitive models to now understand the semantic components of these memory change with impairment tasks. And I should acknowledge up front, this is all in collaboration with my fourth year graduate student, Holly Westfall. So the first semantic task that we looked at is one people get in an instrument called the mild cognitive impairment screening in clinical practice and in diagnosis. And it involves these sorts of triadic comparisons where you're asked to choose the odd one out of elephant and cow and giraffe. And I should emphasize this is just for you to visualize it. Actually, the way it works is the experimenter reads out those three animal names and asks you which one of those three is the odd one out. So just like in Sesame Street, you have to say which one of these is not like the other one. And so they do 12 comparisons like this, just 12 trials per person in the test. They get 9 different animals, but they're drawn from a larger pool at random of 21 different animals that are overall used in the test. And we have a very large clinical data set. So we're going to be talking about 15,000 assessments here from 3,500 people roughly. And these people are independently diagnosed as a sort of ground truth level of impairment. So this diagnosis of impairment is not related to the memory test tasks they do. It involves the clinician talking to the person and their caregivers about their daily functions. This is what's called a fast stage. So each of these people comes with a classification, and there are these 6 different stages. Stage 1 is healthy, unimpaired. Stage 2 is there's no objective impairment in your memory, but subjectively you feel like your memory is starting to fail you a little bit. You're starting to be worried, and some of us can relate to that. Stage 3 is you have mild cognitive impairment. So maybe now you can't do the tax return or complicated financial planning or things like that as well as you used to be able to. And then you move into various stages of dementia in 4, 5, 6, so that you're progressively not bathing appropriately, not dressing appropriately, and so on. And by stage 7, you wouldn't be able to do a task like this. So we have these independent sort of ground truths about the level of impairment somebody has, and we have their performance on this semantic triadic comparison task that is about the meaning of those animals. And what we noticed is there are definitely changes in people's performance across the fast stage. So this graph shows you how often, for example, rat or zebra was chosen as the odd one out across the fast stage, and you can see those patterns are changing. It's not a constant. Something is changing about the triadic comparison judgments as impairment worsens. And if you look at individual triads, you can see changes. So for that elephant, cow, giraffe one I showed you, healthy controls usually choose cow. Maybe that was the answer you thought of. But at mild cognitive impairment, people choose giraffe or cow about equally often, and demented patients choose elephant or cow about equally often. So they're making different decisions. And I guess the challenge is to understand in a model-based way, what is this telling us about the changes in the semantic meaning of these stimuli as impairment progresses? So there are some competing, yeah, Mike.
Just a quick clarification question. This task, when the subject makes the triadic judgments, do they see a series of same category triads one after the other, or are they switching categories?
Okay.
Is it multiple judgments?
So the question is about what's the nature of the 12 triads that they do. They get a set of 9 animals, and then in a balanced way, they get a sequence of triads that involve those 9 animals. And the balance means they see each of the 9 animal pairs equally often on average across the length of the sequence. So it's all animals, and for this person, actually, it's just 9 animals. It's a set of combinations involving those 9.
So on any given trial, they're going to entire trial would have been possibly some of the same animals mixed in with others.
Right. So the question was on the prior trial might well have had some of the same animals. That's true. So it's a balanced design, but this is an example of what you might call, incidental experience of the animals rather than some sort of intentional learning. And we'll come to that later.
Great, thanks.
So there are a number of competing theories to understand what might be changing with the semantic representations here. One really prominent theory, Agnes Chan and colleagues, there are some papers listed there, is that there's some fundamental change to the semantic representation of these animals that happens with impairment. And I guess a Piagetian sort of interpretation of this might be that people reverse the early in development learning as they start to unlearn or become impaired with these things. In particular for the animals, there's an idea that people might stop focusing on abstract properties of the animals and start focusing on very concrete or physical things, like whether this animal is large or whether this animal is dangerous or something, that those become the important parts of the representation later on with impairment, whereas more abstract things like, do these live on a savanna or could you find them in a zoo, might be part of the healthy representation. The competing idea is in one sense the boring one, but it's a serious competitor, which is the representation doesn't change. It's just that your access to the semantics becomes noisier, and so that impairs or affects the judgments in some way. And that's being promoted by a number of people. So let's think about how those competing hypotheses would play out in this triadic comparison task. Here's the triad that I showed you already, and we're thinking now of these animals being represented in terms of a number of features, and those features being given different attention weights or saliencies, how much that feature matters. So just schematically here, we're imagining fat, giraffe, spot for Africa and zoo as potential features. Blue dots mean those animals have that feature in somebody's representation, and the size of the dot is how much weight they're giving to that. So this might be for the healthy people, and you can see Africa and zoo are given a lot of weight here, so that would make the elephant and the giraffe very similar, and so people would probably choose cow as the odd one out under this representation. So under that first idea that representations get restructured, that probably comes in two flavors. One would be that you lose some of the features. Maybe you just don't know about Africa and zoo anymore as potential features, and so you have to concentrate on features like whether they're fat and whether they're a draft animal, because that's what's left. And that could bring cow and elephant close together, and now you'd be choosing giraffe as the odd one. That would be a restructured representational account. A second version would be attention change, which is another form of restructured representation, but now you don't lose the features, it's just you attend to them in different degrees. What you were paying attention to changes as impairment progresses. So now all the features have been brought back, but Africa and zoo don't have very much attention anymore. Instead, the weight is being given to things like whether they're fat and whether they have spots or something like this. And that might bring cow and elephant together, and you would be choosing giraffe as the odd one. So all the features exist, but you've changed the attention that you paid to them over time. And the third hypothesis would just be that noisy access one, which is just everything gets blurred. It's all the same information, but you're more stochastic in the choices that you make. So my graduate student likes to put it this way, can we model this? Can we find a model-based approach to address this problem? And their answer was, you bet giraffe we can. We worked a long time on that. I thought I needed to share with you. So in a classic math psych cognitive modeling sort of mode, we're going to build models that a basic model and then tweak that model to represent each of those three hypotheses, the representational restructuring, the attention change, and the noisy access, and see what model-based support there is in the data for each of these conceptual possibilities. The basic model I've really already anticipated. If you just think about the similarity between pairs of animals as being something that a person knows, the semantic similarity between each pair, then you're more likely to choose cow to the extent that elephant and giraffe are highly similar to each other. So you're more likely to choose A if B and C are very similar to each other, normalized by all of the similarities. That's a simple probability matching choice rule. It demands that you have some ability to measure the similarity in the first place, and I've anticipated this. The idea is that there's a set of features that, and we know whether animals A and B have those features, and their similarity is the sum of the weights of the common features that they share, as per Shepherd and Araby in the contrast model, and Tversky's seminal work. So that's a natural choice and representation model, it also demands that we have some way of knowing what these features might be. You could do this in using something like additive clustering and try and discover them or infer them. A simpler, more direct way is to take lists of features that have been generated as part of norm databases, and in particular we use the Irvine Natural Language Concept Database, which involves, you can see a subset of it here, a very large number of features that people have generated as potential things that might represent the animals and whether or not each of those animals have. So we use this database. We needed to clean it up a little bit to remove redundant features and to extend it to a couple of animals that weren't already in the database. But this is what we use as our potential feature set. So using that basic model that says how things are represented and how choices are made, what would the representational restructuring hypothesis look like? Well, the idea now would be that people are only using a subset of the possible features in each of those fast stages, in each of those levels of impairment, that the set of features were changing, things are being included and removed. So this Z parameter is a binary parameter that says whether or not a feature is being used in the teeth stage. And so this is an indicator variable with some sort of base rate. Actually, let me correct that. So now the W is, well, yes, sorry, I mucked myself up with the notation. So Z is exactly what I said it is. I was being thrown by the towel light. So Z is an indicator saying whether or not this feature is used by people in the teeth stage. Is this a feature that people use? And the tau is indicating whether that feature has changed from one fast stage to another. So tau is like a flipping parameter to say whether fast stage 3 used to use it, but fast stage 4 doesn't, or they didn't use it and now they do, so it's flipping back and forth. And so this is a model that we can apply to the data. All the models that I'm applying in this talk have been implemented as Bayesian graphical models in a language called JAGS, which I like to use a lot. And that has the advantage that everything is being done with fully Bayesian inference with computational sampling methods. And I won't say any more about that. That's just like a basic demand of all of the modeling that we do, because it allows for this fully Bayesian inference method. So what we find from the Z parameters first, remember this is the set of which features are people using and not using in each of the stage. Here's the posterior probabilities and the number of features that have these posterior probabilities. So if we look at stage 1 and 2, you can see that there's almost zero probability, almost no probability that about 60 something of these features out of the overall 120 odd in the Irvine database are being used. But there's about 40 something that we're very confident are being used. And there's almost no uncertainty in between. It's like a hard classification that these are the features being used and these are the ones not being used by people in that stage. And then you can see the inference for the other fast stages, and you notice these look remarkably similar, that there are 40 something features being used by people in every one of these fast stages. That doesn't prove, of course, that they're the same features. It just means it's the same number of features. That tau parameter that was tripping me earlier does tell you that, and tau has a base rate phi, and here's those base rates. So a low base rate here means nothing is changing. That's shown by the posterior distributions in blue against the prior in yellow. And this is for the transition from healthy to mild cognitive impairment, and then from mild cognitive impairment to the various stages of dementia. So what we see in these posterior distributions is a lot of density around 0. That's density that nothing is being flipped, nothing is changing. In fact, these are the same features. Sadiq.
Are there correlations between the features? I'm sure there are, but there might be potential some redundancy. Well, you can imagine the feature that have for another one.
Yeah, so the question was about redundancy in the features. Of course, there's massive sorts of collinearity. The only thing we did was remove ones that were literally exactly redundant. So if they had exactly the same pattern of belonging and not belonging to an animal, to the set of animals, then that doesn't convey any information, and we just picked the highest frequency label and called it that. But that's all we did. And I think that's right, because this is a natural structure. So being able to be a draft animal is correlated with being large. That's how you can drag things around. So we want that structure in there. This is presumably part of the meaning that people have.
But I guess kind of as a follow to that, is there the potential that some systematic correlational structure feature influences the how many features are?
Yeah, okay, so could these collinearities be a problem in the inference that we're doing under the model we're doing? Absolutely. And if this hadn't worked out so nicely, which is what it did right at the beginning, we would have had to have investigated those. But this is very clean. This says out of the 120 odd features, people are using about 42 of them. That explains their behavior very well. And it's almost exactly the same 42 for all of the stages. So maybe just by happy coincidence at that point, we're nicely done. And so the conclusion here would be this is pretty strong evidence against that representational restructuring hypothesis. We've allowed for all of these features. We've allowed for them to change in arbitrary ways. We see people consistently having their triadic choice judgments explained by the same set of features without anything flipping from stage to stage. So what about the other form of attention change? This is the other form of representational change, which was this idea of change in attention. And this has been promoted by Chan and colleagues again. Their specific idea is to think of features as coming in three different types, or at least this is one version of the theory. So these three different types are physical, so these are properties, is it fat, does it have spots and things like that. Abstract ones, which is kind of the capabilities of the animals, like does it eat nuts, can it swim, and things like that. And then thematic ones, which is kind of the roles that it takes. Is it a cartoon figure, or can it be a pet, or what sort of role does it take? So we went through and classified the 120 features into each of those thematic categories and had a number of raters do it and resolve disagreements with a third rater and so on, and came up with a set so that we were dividing the features into those three types. And now the idea is that the attention weights for each individual feature is drawn from a hierarchical distribution, but that distribution is divided up by the taxonomic types. There's one distribution for physical type features, one distribution for abstract, one for thematic. Each feature gets a weight that's drawn from that distribution. And then we're interested in whether the means of those distributions are changing systematically with impairment. So that involves another sort of hierarchical model where you regress the nature of the attention weight change across the fast stages. And in particular, we're looking for a pattern of change that is the one predicted by this Chan et al. Theory, where they would say the physical features are being attended to more. So the slope of the line for the change in attention should go up for the physical features with impairment, and both abstract and thematic should consequently drop. So there's a very specific sort of ordinal prediction on the slope of the change, the rate or nature, the qualitative nature of the change of the attention weights to these different feature types. So we applied this model, and see this is another big hierarchical model that can be implemented in Bayesian ways. And here are the results we get for the means of those three types of features across the different fast states. You can see there probably is some change, and you can get Bayes factors to back that up if you like, but the change is not of the type predicted by the theory. In particular, all three types of features are just attended to systematically less. It's not that the one for abstract, for physical, the green is going upwards. And again, you can get a Bayes factor for that. For the specific hypothesis, the slope goes up for one and down for the other two. That's an order constrained Bayes factor you can calculate, and the evidence against that is these data are 35 times more likely if it's not that than if it is. So fairly strong evidence against this attention change hypothesis, which would say all of the features are available, but the way we attend to them. So that leaves the final theory, which is the noisy access hypothesis, that everything just blurs. And at this point, we introduced two extra bits to really the decision rule. So nothing's changing in the representation, but the decision rule now should be sensitive to the noise or be able to measure the noise. So one parameter we introduce is this determinism parameter gamma. You can think of, if gamma is 1, you get back to probability matching. If gamma is a very large number, you deterministically choose the animal that is the least similar in the pairs. And as gamma goes towards 0, you get random responding. So as gamma decreases, you just get noisier in your judgment. And the second thing we did was introduce what we call a recency parameter. It doesn't mean the same thing as in some memory tests. It means imagine you're impaired in doing this task and you get cow, elephant, giraffe. It's your tendency just to say giraffe, the last one that you heard, because this is a challenging cognitive task at this point. So this beta is something that upweights the probability you just respond to the last animal in the list and consequently downweights the others. So we applied that model. Here are the results we get, first of all, for determinism for healthy people moving through impairment to dementia. And you can see things are becoming less deterministic. It's moving closer and closer towards probability matching and down towards chance responding below. And you can see Even healthy people have a recency bias because the base rate here should be a third for the three choices, but that recency bias is growing stronger. And again, Bayes factors back this up. So an interpretation here would be, this is consistent with noisy access where people are becoming less deterministic, less literally driven, if you like, by the similarities in the odd one out choices that they make, and almost compensating for that, they're tending to choose the last animal more often. Yeah, so the question is, are people consistent in their judgments across the task themselves? It's a little difficult to judge based on just 12 triads. That is a very impoverished experiment because this is one task as part of a very large battery. And so I think the honest answer is it's not really enough data to tell. At the level of subgroups, so if we took all the fast stage 6 people and developed some representation of what they think, that seems to be reliably different from what fast stage 3 thought. So there's at least some within group consistency. And I guess if you measured them longitudinally, and some of them do the repeat tests, so we could look at this, but we haven't, we could then test whether that within group is also within individual. A little tricky in real world data though, because of course you're trying to hit a moving target. People are becoming more impaired longitudinally. Tricky to Yes, so doesn't the recency bias just imply they'll be inconsistent? Yes, so that's another way of saying noisy responding. I think noisy access might not even be the right word. I think the key thing is that it's not evidence of a fundamental change in how you represent the animals, either in terms of the features you use, the dimensions you think about them on, or the level of salience or importance that you give to those dimensions. So I've kind of already said all of these things. In those 3 modeling examples, we don't see any evidence for change in fundamental representation or for change in attention in the systematic way predicted by the theory, the Agentian idea, but we do see evidence for access or the use of representations becoming noisier in the choice process. Are there any other questions for anyone? Yeah. Yeah, wonderful question and a great idea, and we haven't looked at it, but let me just reflect back so I understood it and really appreciated the question. You could well imagine that similarity in these features and these attention weights are not just latent things that are sitting there, they're generated in context as for so much of decision and choice and preference and judgment. And that dynamic process could have sequential effects or could have all sorts of other interesting stuff. I think as per the answer to the earlier question, 12 triads is probably not going to let us investigate and unpack that, but this is where we could go and do an experiment with healthy controls that's much longer, try and build a good model and apply that back in. I think it's a wonderful way. The second thing they do in this, that's semantic in this mild cognitive impairment screen, is a surprise free recall task. I didn't tell you about it because they didn't get told about it, but they went and did some other stuff and then they came back and now it was, how many of those 9 animals that you studied, how many of those can you recall? So they weren't told to study this, they just asked if they can do it. So I think this is a really interesting way to study free recall because as per an early answer to Mike's question, this is an example of, I think, what memory people call incidental rather than intentional learning. You weren't given a list and studied it like for an exam. This is more like cooking with 3 spices in this dish and then 3 spices, perhaps one of the same ones in the next dish, and then going to the grocery store and thinking, which spices do I need to buy? I've been encountering these as part of my everyday activity in some interesting jumbled way over the last little while. And it also has an interesting property in that some of these you've encountered more often, or they've been repeated more often to the extent you gave them as the odd one out answer. So you can see down here, this is what the pattern of encountering looks like. You're going to recall at time 0, but 4 minutes ago or something, you had a triad where 3 of them were read out to you, beaver, cat, deer, and then you said beaver. So you've now heard beaver twice as often as the other 2 because you answered using it. Then there's a little space and then you get another triad. And in fact, there's even a little gap between the 3 triads and you generating the answer. And so you've had these 12 triads with the 9 animals, and you've seen all of these things in some interesting interjumbled way. This isn't a standard setup for a free recall task where you just study something that has clear and obvious primacy and recency from the first items and the second items and so on. But you can do some of that sort of analysis to see what regularities there might be in the data. So this shows by the first triad that an animal appears in, and now we've broken people down into these are fast stage 1 and 2. This is fast stage 3, the cognitive impairment, and this is 4, 5, and 6, the dementia. So maybe there's a, well, I don't see any, I guess you could call it primacy effect, where the first triad, where it was first presented, which could be anywhere between triad 1 and 9, it couldn't be on the last few because of the balanced design. That doesn't seem to be having a big impact on the probability of recall. Maybe there's a tiny recency effect with the last triad. Maybe that's edging its way up a little bit, so a tiny bit of recency potentially. And study encounters, that would be another way of saying repetition. You have to encounter it 4 times because it's in there 4 times. But if you always gave it as your odd one out, you would have encountered it 8 times as part of the repetition. And that does seem to make a difference to the probability of recall. So we want a model that tries to deal with this. I might be in hostile territory now, because now I'm going to propose that the simple model is a useful, almost certainly wrong, but useful model for doing this, because it has the 3 properties that I was just talking about. The idea in simple is that you lay down a memory trace on a timeline every time you encounter an object, and that timeline is then logarithmically compressed, and that's what gives it the scale invariant properties that there's some evidence for. So you can think of it as these posts running along a beach. This is the last thing that you said in the answer to the last triad, and here were the 3 that were presented to you on the last triad, and here are all those other triads running back in time, getting progressed and progressively harder to tell apart. So this has a little bit of recency because it's easier to see that one than it is to see something way back there. Primacy, I mean, almost nothing. I guess the one that's right at the beginning doesn't have anything further behind it, but my eyes don't work that well, so trivial if it's there. And then if these were different colors or something corresponding to the different animals, so that there was a red one for beaver face, then the more red ones there are in there, the greater chance you've got of being able to see at least one. So that was the intuition for using simple. And so that means the representation that I just showed you, this is the physical representation of time. This would be the mental representation with the logarithmic compression. And you can see the equation for the logarithmic compression here. Then the idea is people's acuity in looking at that representation is one of the key parameters lambda. So here's a person with poor temporal acuity. They're trying to retrieve from something in this triad, but their acuity is such that they could really get back from that attempt to probe anything within the triad. There would be anything falling within this gradient. And that gets even worse for things that were presented in the early triads that are more compressed and harder to see. Here's a person with a higher value of lambda and so more temporal acuity, if you like, closer to 20/20 vision or something like that. And so they've got some chance of getting the right thing, and they're certainly going to get something within this triad, and they've even got a shot of doing it for one of the harder ones further back. So that's the first parameter of interest in temporal model with this representation, and then it has some normalization across all of these temporal distances, the A's, the S. But of course, these things are not just temporally presented. That was the whole point. They've also got semantic representations. So here's a multidimensional scaling of an accepted set of similarities, semantic similarities between these animals, so that more semantically similar animals are near each other. So this gives you a model of or a measure of the similarity between each pair of animals in analog to the measure of temporal similarity that we just extracted by probing on the compressed temporal representation. And so now the second parameter of interest would be how much weight do people give to both of those different components? How much weight do you give when you're trying to retrieve to how long ago you heard this? Like I remember the experimenter reading out cow or whatever animal that it was, and I'm trying to get that back from my temporal memory, versus I was just thinking about sheep, and so now goat is coming to mind, some sort of semantic-based retrieval process. So omega is going to be the second key parameter, where omega of 1 means you're giving all the attention to the temporal study and nothing to semantics, and an omega of 0 would be it's all about semantics. And then you need to do some classic math-like stuff to map that out to actually make predictions about behavior in the experiment. This is following what the people who developed the simple model proposed. It's basically the idea that An attempted retrieval has to be above some threshold level, and that threshold has some noise. So you have a standard logistic function to do that. And then the probability you get a particular temporal trace back is that you got it back at least once in all of your probe attempts. And then the probability you get an animal back is at least one of those retrieved instances was representing that. So just trust me, that math all plays out so that the model now makes predictions about behavior, and we can apply it to the data. So we were interested in those first two parameters. I emphasized the temporal acuity, how precisely people could see their memory as impairment progressed, and how much emphasis they gave to semantics. So we tried a model that loaded all of the explanation on those through hierarchical distributions for the three different stages, the healthy, the impaired, and dementia patients. And we let the threshold and the threshold noise be constant because we were less interested in the explanatory burden falling on those parameters. This turned out to be a reasonable thing to do in our first analysis, and this is the first, what we hope for more. We had 100 healthy, impaired, and dementia patients, only 100. We have many more, but the model is computationally expensive to run. This model turns out to be descriptively adequate. So this is showing for all of the times where we predicted, where the model expected there to be a 20% chance that the animal name would be recalled. In fact, those animals were recalled 20% of the time. So the model is well calibrated with the data in that sense. We discovered that the threshold was very high, but it was quite noisy. So it's facing strong demands if we really want to be getting a strong signal back before we act upon this, and that's pretty much always the case. So those are just preliminary results. This is the interesting result. Preliminary ones I've put over there on the right. This is the interesting one, which shows the joint posterior distribution for the mean temporal acuity on the x-axis and the mean weighting given between semantics and temporal information on the y-axis. So it's the posterior distributions of the means for each of the three groups. So in blue, we have the healthy people. This means they have the best temporal acuity. They have the sharpest one of those lambdas able to probe the memory, and they're giving about 50% emphasis to both temporal and semantic information. So both what I heard when I was presented with this, but also semantic cueing or the use of semantic information to recall other animals. As people go to mild cognitive impairment, it looks like, and so this is only a preliminary claim, but it looks like most of the hit you take is in the temporal information, that you're less well able to remember the details of the words being read out to you in the test, but the semantic information is still intact. And then as you go to dementia, you lose both of them. But the semantic information is lost in the demented patients as well as having very poor temporal acuity. I have a couple of other sort of very preliminary results of last week I can show you that suggest that that pattern is even stronger. This is the result that I trust enough to sort of present in an archival way. But it looks like that's right. First of all, there's a hit to the temporal acuity, and then there's a hit to the semantics. And let me just mention where we're going next as a way of wrapping up. This is something like the multidimensional scaling representation that I showed you before, but now with everything just drawn on a circle. So these animals are roughly located according to their semantic similarities. Now we're looking at not just what was free recalled, but the order in which it was free recalled. So if people recalled 6 animals, what was the sequence that they recalled them? The arrows here show the thicker the arrow, the more often that sequence was made. So for example, you can see lion followed by tiger was a very common recall sequence. Actually, tiger followed by lion was less common. It happened, but it was less common. So these are like semantic conditional response probability curves, except even with a little more information, because you can actually see the semantics of individual transitions rather than just collapsed over the absolute measure of similarity. These would correspond to semantic CRPs that bumped up right at the end, because the transitions that are being made are along the circumference between very similar animals. Semantics is driving this recall sequence. That's not true as you become progressively more impaired. So I was just showing you stages 1 and 2. You can see, especially for the moderately and severely demented patients, that semantic structure is being lost in the recall, and to the extent they recall words, they're being made without respect to semantics. We wondered whether there was anything systematic that was happening that wasn't semantics. Maybe it's something else like age of acquisition or frequency in the language. We tried everything we can think of. So semantics definitely matters, but matters less as you become impaired. This is the repetition effect, which is having some impact. Everything else we could think of, word frequency, word length, age of acquisition, emotional valence, whatever it is, it's not those four things that's driving the difference in behavior. And so it's an open question for us, what might be driving the behavior. Otherwise, we're back to the default explanation of it's just noise. We also need to model this, and we actually suspect that simple might not be the right way to model these sorts of things. So I want to finish up by making 4 points. I think the overarching story we get from this, maybe you view this as a negative one, but if it's right, it's the only alternative, which is that the big grand idea that representations are changing in some interesting structured way, we just haven't seen any evidence for that in the triadic choices or in the free recall or in the order of free recall. And so we're skeptical about that idea. We think that means that other sources of evidence that we haven't directly examined, like from verbal fluency tasks that make similar claims, they should be looked at in a similar model-based way to see whether evidence could be found. A really strong, and I would love to do this, a really strong extension and a really strong test of our approach would be to reverse this developmentally, because our prediction would be everything that was noisy access here and was a kind of uninteresting explanation should become very interesting in children as they pick up and learn the semantics. So if developmentally they could do all of these tasks, we would now expect to see there is representational change. Now they know what a zoo animal is or a savanna animal is. Very strong test of the model. And then finally, harking back to the solution-driven science that I started with, I think at a minimum, all of this is useful if you think about wanting to measure and diagnose and understand memory in clinical settings. You could imagine those groups I was showing, if people were doing some sort on some drug regimen or doing some exercise routine, this would be a way of measuring whether those different groups in an experiment, how their memory was changing, their access to semantic information, their temporal acuity, the emphasis they were given to semantics, and so on. Okay, so I want to make sure I acknowledge again Holly Westfall. This really is all in collaboration with her. Effectively, I've just given her thesis defense, sort of. And the people at MBIC, so this is the medical informatics company, Jason Dennis Rod, who none of this would have been possible without. And thanks very much to all of you for your attention.
There is a question in chat, so it's probably
Does that mean finding it? Can you read it out to me?
Okay, I'll read it out. So then you have to repeat it first. Oh, there you go. So how dependent is star solvent? Yeah. How dependent are your technical functions results on the future category? For example, I don't think really understand the abstract category. Example, where the semantic category. Have you done now?
Right. So no, we haven't done it on an individual feature level. I don't think an individual feature level would make sense. That would be like 120 lines going in different directions and would immediately demand how would you group these together. But I do accept the bit that those groupings are one take on verbally stated hypotheses in the papers we're addressing. This was our best attempt to take their definitions and their examples and map them to a concrete set of features we had. We did at least try and do things minimally correctly where people independently went away and broke things into the categories based upon these definitions. In very large agreement, we only had to resolve sort of 4 or 5 out of 120 when it all came back together. But does that mean we did it exactly right, or that their verbal description really should have been taken as literally as we interpreted it? Absolutely not. So it would be interesting, and you could do this in 2 ways, to look at other definitions of different taxonomy of features and see whether some signal emerged from that. That would be extremely interesting. Or you could try and discover this from the data. You know, let's propose that there are 3 categories, and we want to find 3 categories such that one systematically goes up and the other 2 go down. What would such categories be, and are they interpretable once we see that these features are being petitioned in this way? Those would both be interesting things to do.
So I want to say so I'm wondering if to what extent you really think that this is about representation access or is it about noise from because if you imagine representation, it's not like you can easily like get rid of one feature every then as you get to generation, that's one feature.
Yes.
So what's going to happen is that you'll
Yes, yes.
So that kind of is, I mean, let's just say for the sake of argument, like, how do you think that kind of knowledge?
So the question, if I got the essence of the question for people on Zoom, it was, you made one set of fairly strong assumptions about what semantic representations might look like underneath, and all of your results are conditioned upon those assumptions. What about some other assumptions? I think that's perfectly valid. And in fact, some of the claims made that we're addressing, I don't think any of them used exactly the feature-based representation we proposed. Many of them used multidimensional scaling or pathfinder or graph network or other sorts of representations. So it would be natural to try those. I do think that it is very unlikely that we represent animals in terms of a small number of continuous underlying dimensions, which is what some of those other representational structures would assume. I do think featural and common featural similarity, there's a lot of evidence for that, and it feels right to me. I can show you a graph that here's the descriptive adequacy of those representational models. And so the red one is showing that things change, but ones that are colored are for the substantive hypotheses. These are very descriptively adequate accounts of the behavioral data. So it's at least, what we've presented is at least one good model, but that doesn't mean that there isn't some other representational structure. I think the graph one would be the most interesting if I was going to pick another one to work on. That would provide a different window onto what these memories look like. And if our result is right, it should be robust to those sorts of changes in the representational assumptions, and that makes it important work to do. So I'm agreeing with you. There was one here.
So we're wondering if an item level feature over time to model in the different access to a certain size, there's difficult and difficulties on that.
So the question was about item level differences. I think at some point, and item level might be about that point, we would probably need richer information to get any traction at all. And so maybe this also partly goes back to Anna's question. If, for example, we had response time distributions that we trusted, that would be additional information that would help you try and distinguish, and maybe that would help distinguish whether it's access to the representation or some final decision-making strategy that is changing the response behavior and so on. We're able to do a tiny bit of that here. That recency parameter is an example of trying to unpack things like that. You could even imagine that, for example, could be animal specific, so that if you heard zebra last, that has an even stronger effect than something else. But I think we would need more informative data. You could always do the analysis, but if the posterior you get back is that could be true and the probability is somewhere between 0 and 1, then your data just haven't had enough information. Yeah.
So Michael, great talk. I love the idea of bringing that site to the world of clinical decision making. And I guess I'm going to ask the question, have you thought about taking this to the next step? Maybe you've already done this. Presumably the stages come from a variety of other clinical tests, right? That determine whether somebody is stage I or stage 2. Now you have your memory task and your triadic judgment task, and you can extract basic behaviors from those tasks the way a neuropsychologist would, and use those numbers to forecast stage. Or you could fit the detailed sequence of responses using your math model and use the parameters of the math model to pick the stage. Are we ready to think about whether the math model adds valuable predictive power above and beyond just measuring? If you recall, how many words did they remember?
Right. So the question was whether the sort of parameters, these latent parameters that are being inferred by this whole model-based approach could be useful for understanding first and predicting ultimately the fast staging that is the sort of clinical measurement of impairment. And I think the answer is that is where we would like to go, but we're not there yet. It's important to understand how different that fast staging is from the memory test. The beginning of your question said, on some other tests, they do some things, but it's not really that. The clinician works this up by interviewing the patient and caregivers. So it's really, do they always keep appointments on time? Do they dress appropriately? Do they bathe? Were they able to do their tax return independently? You know, these are not memory tests. This is the consequences of your memory for functional assessment in everyday living. So that's a very lofty goal to predict from the sequences of tests. So I think what I would say is that starting motivation, where I've moved away from strictly episodic elements of the testing to now at least incorporate some semantic component, that's got to have moved to some small increment to being able to make those sorts of predictions. But I doubt that it's sufficient. You know, I'm sure understanding all the elements of these tests and being able to extract latent parameters like how much attention they pay to semantics, that's an important part of figuring out whether they can do their tax return or bathe appropriately. But I'm sure we would need additional information that is somehow implicit in the test performance before we could do a really good job of making it.
So I just do a quick follow-up. So I completely see that point, and I would expect the correlation would be weak, right? It would be weak for both the gross index of behavior and the model-based parameters would be weak. And the idea is the model, as we've shown, imposes some structure that would be more sophisticated power to use the data to make it. But at the same time, the model requires estimation from the data.
Yes.
And so a technical version of my question is, how do we have any basis for imagining the trade-off favors the modeling, insofar as even if the model possessed structure that would be helpful, if you fit in the model to an individual participant, the estimation there is large. It would swamp the benefits of the structural assumptions imposed by the model. I don't have a sense of how you.
Right. So the question is, data collection for this is expensive and time consuming and sparse and it's self-noisy, and modeling is hard work and the models are imperfect. So by the time you've combined those two things, have you really made any, was it worth all of that effort to get there? Really hard question to answer in general. If I had my way, we would be assessing people in a unobtrusive, naturally occurring way and have rich data sources. So if people are on their smartphones all the time, presumably they're doing things that are reflective of their ability to remember something that happened a little while ago, or the semantics they have between things. If you had some online data source that was continually pouring in so that this assessment was happening all the time, this potentially addresses both of these problems in some way, because you now have a cheap, almost free, rich data source that is relevant, and it contains more information. It would have the sequences of response times and all the other rich information, so you could potentially build models that will still be wrong, but will be getting progressively more useful, and you could try and solve the problem that way.
You mentioned at some point that there was that seems inconsistent with the idea that
well, yeah. So, but if you reverse that, you know, as the noise goes back up into structure, that's consistency at the higher stages. But I agree. I probably overstated that. If there is a strong regularity to the impaired representations, we don't know what it is, but it's consistent in that impairment, if that makes sense. It's not like there's a subgroup who are behaving normally and a subgroup who are noisy or something. So it's fairly weak. And actually, there's one exception to that in fast stage 5, and this was some modeling I didn't talk about here, but we had to do. In one of the fast stages, it's possible to perform very poorly on the memory test, consistent with sort of mild dementia, but not because you're demented, because you're highly depressed. And so that has very different possibilities. It's possible to be in that fast stage because you're depressed, but your memory performance is still qualitatively different from the other people in that fast stage. So that would be an example of inconsistency. And I'm saying in these data, we don't see that.
That both tasks were administered to the same subject, right?
Yes.
the fidelity of
Right.
the noise that but noise is really what's going on.
So the question was, you treated these as 2.5 separate modeling exercises for the triadic comparison, then the free recall, and then the sequences of recall. Shouldn't this all be one big model, or at a minimum correlate the things that should mean the same thing across tasks? Absolutely. I mean, we're 2.5 in, and then we'll get to 3 where we've got individual models of each of them, and then this should all come from the same system and be driven by the same processes, maybe with some regulatory variables. Your approach to accessing the semantic information you have is driven by different contextual demands in triadic choice than it is in free recall, but it should be addressing the same system. Should be able to say that's ambitious, but that doesn't should be kind of. Yeah.
Helping people and walk them down the road by training them into the way, by corrupting them.
Yeah, so the question was, should we, or maybe one way of asking it is, should we test the idea that the behavior is just noisy based upon the same representations by putting healthy people who we assume have the right representations in conditions that make noisy responding all they can do, like time pressure or cognitive load or something like that? Yes, yes, or give them impoverished training in the first place rather than the output demands. I don't know, first time I thought about it. What I would find really interesting in that is, to what extent are there compensatory strategies where there's an important decision-making element where people are compensating? The recency bias was the one I showed you, but there are potentially many others where people have a metacognitive understanding that their memory system is failing in some ways, and that leads to behavioral changes that are driven by decision strategies or whatever they are, because the experiment you just described should distinguish those two. The healthy people shouldn't have developed those strategies because they haven't been living with this. They'll cope in some way, like a speed accuracy trade-off or something. And it would be interesting to see if there's qualitatively different decision strategy behavior in the people who have been living with impairment. And I would love to separate those two out. It comes back to questions about whether it's noise of access or in the responding. My guess is we don't pay enough attention to the compensating decision strategies, sort of viewing the person as part of a overall self-regulating system, and this would be a window onto that. The child development angle would also be another way of getting this. Thank you very much, folks. Appreciate it.